We're now going to consider a model of cyclical behaviour that is not a simple harmonic oscillator. So in the natural world, it's observed that there are cycles in the populations of predators and prey. The classic example is rabbits and foxes. So the foxes eat the rabbits, and when there aren't many foxes around, the rabbits can breed and their population increases and they undergo a population explosion. But that means that the foxes can feast on the rabbits, and so their population grows. And as the population of the foxes increases, they're eating lots of rabbits, and the population of the rabbits starts to decline. And because the population of the rabbits declines, then there isn't enough for the foxes to eat, and so the foxes' population declines. And so both populations can crash, and you end up back at the situation where there's not many foxes around, and so the rabbits can breed and the whole thing starts again. Now we might think, cycles, simple harmonic oscillator, sines and cosines and that sort of thing. We know the kinds of equations that will generate that kind of effect. But the trouble with sines and cosines is that they go negative, and we can't have negative rabbits. And so this situation is modelled with what are known as the Lotka-Volterra equations, after the two scientists who developed the model. And they look like this. So what we have here is, if we say X is the prey, the rabbits, and Y the predators.
A, B, C, and D are constants.
Each population tends to increase according to an exponential law. So we're basically saying that X dot equals R times X, the rate of growth times X. So it would increase exponentially. That's a natural thing for populations to do. Except that this R depends on the population of foxes. So we're replacing R with this expression, which is saying that if there were no foxes, Y represents the foxes, the predators, then the rate of increase of the rabbit population X would be positive, because there's this constant A and it's shown as a positive value. So it's saying that the births of the rabbits would outweigh the deaths in the natural condition. But there's another factor increasing the deaths of the rabbits, which is that they're being eaten by the foxes. And this is what this term represents. The more foxes there are, the more rabbits are being eaten. And so that decreases their growth rate. And then for the predators, we say that, again, we've got something of the form Y equals Rx, would be a different R in this case. Whoops, Ry. But in this case, R here is represented by Cx minus D. And what this is saying is that if there were no rabbits, so if we ignored that, the natural rate of increase of the foxes is negative. So if there's nothing for them to eat, the deaths of the foxes would outweigh the births, so their population would decrease. But if there were rabbits, then that adds a factor to the births of the foxes, or at least reduces the deaths of the foxes. And the more rabbits there are, the more the foxes can breed or, prevent themselves from dying. So we end up with those pair of equations. Now we can find that there is a point at which they would be in equilibrium, because if A minus BY is 0, then the prey population would not increase. It would be 0 times X, so it would stay the same. It would neither increase nor decrease. And if the this thing Cx minus D is 0, then the predator population won't change. So that situation will occur if we have that from here x equals d over c and y is equal to a over b. If we substitute those in there, we get cx times d over c would just be c times d over c. D minus d is 0, and similarly for y equals a over b. So there is a point at which they are in equilibrium and the two populations would just stay the same. But in general, if they're not at this particular balanced position, then the populations will change over time according to these equations. Now, these equations can be solved, and you know the solutions aren't that difficult, but they're not that pretty. And usually systems like this are studied with computational methods, so we just simulate them. And I should say that this is a simplest form of the Lotka-Volterra equations. There are other versions where we add other terms to represent other kinds of effects that one can imagine, or you may even have, you know, more than two species interacting. So the equations can become very difficult to solve. So they tend to be studied with computational methods, which means you just feed the equations into a computer and it simulates the changes in the population, just stepping them forward in time. We'll discuss computational methods later in this mathematics module. And if you do that, then you get something like this. We have cycles in the populations of predators and prey. These represent their populations. The prey population here is shown in black and the predators in red. So you can see that when the predators population is low, the prey starts to increase, but that's causing the predator population to increase, and at this point the predators are overwhelming the prey and their population crashes, and that causes the predator population to decline as well, and then the whole cycle repeats. And while we can study the dynamics using a graph like this, just plotting them against time, another way that people study these things is by plotting the variables not against time but against each other. And that's known as a phase space portrait or phase space plot. So if we do that, we end up with something like this. We're plotting the population of the prey along the x-axis and the population of the predators along the y-axis. And when we're at this point with a large number of predators, y is large, then the prey population is decreasing, is being eaten by the predators, and so it's tending to decline. So we're moving from right to left in this plot. And then when we get to here, the prey population is now small, so the predator population is starting to decrease, is crashing. So we're moving down in this plot. And then we get to here, now the the predator population has massively decreased, so now the prey can start to increase again. And so we're moving now to the right, population increasing. And then up here, the prey is now large numbers, so the predator population starts to increase and we move up. So this phase space plot is another useful tool for understanding and examining the dynamics. And it's found that the period of this oscillation, t, is 2 pi over the square root of a times D, where A and D are these values in the Lotka-Volterra equations. So you can see that that's like omega in the simple harmonic oscillator. So, what has all this to do with theoretical history? We've been talking about predators and prey. Well, it can be that we find situations in socio-historical processes that resemble the predator-prey dynamic, and therefore where we can use equations like this to model them. And an example is some work by Turchin and Korotayev on war and population pressure in tribal societies. And so what they're looking at in their model is that as in tribal societies the population pressure increases, there's too many people for the land, there tends to be a growth in warfare among rival tribes trying to steal each other's land and resources. But the warfare then reduces the population through battle deaths. And so the population crashes, and now there's no pressure on the land anymore, because now the land is perfectly adequate to feed the crashed population, and warfare decreases. And this allows the population to rise again. I'm not sure if I said that it's the warfare that kills people off, and so that causes a population to crash. And then the population is low, no population pressure, warfare declines, population can increase again. And so you go around in the cycle. So it's something like this. We've got population pressure and war. And as population pressure increases, then that causes war to increase. Increase in war reduces the population, causes the population to decline. The decline in the population produces a reduction in warfare, which allows the population to grow again, and so on. They didn't use exactly these equations, they used a modified version of them. But we don't need to go through all the possible variations. We're just interested at the moment in understanding the idea of Lotka-Volterra. Another example is models developed by Dimitrios Dendrinos, a researcher in urban science. He's used this for modelling processes that happen in cities. So one process that you can get in cities is gentrification, and its reverse, slumification. So what happens is that you have a neighbourhood in the city that is poor and run down and not a desirable place to live. And therefore the property prices in that neighbourhood are cheap. And so young, upwardly mobile professionals who are starting out in life but have great ambitions can see that, okay, this isn't a nice place to live, but the property prices are cheap. So let's buy up that house and then we can do it up. And so they do that up and they make it nicer. And more young professionals come in and do the same. And you start to get the general character of the neighbourhood starts to improve as more and more people come in and start doing up these properties, taking advantage of the cheap property prices. And so it converts from being a place that's run down to a place that's nice and desirable, and that is gentrification. And so those young people who have bought those houses, they grow up, they raise their families, they eventually retire, and their houses now come to be sold back into the market. But now, because this is a desirable place to live and people want to be moving in there, the property prices are very high. And so they're out of the reach of the kind of young people who in the past might have been moving into that neighbourhood. And what then happens is that either the children of these people rent out their properties, or landlords buy them up to rent them out. So they divide them up into flats and let them out to renters who are people on lower incomes. The landlords, they don't, they try to get away with a minimum amount of maintenance on their properties. The people living there, well, they're just renters, they're just passing through, so they don't have any particular incentive to do it up, make it nice, so they let the whole place run down. And so you're now moving towards a neighbourhood that's full of these houses converted into flats with low income renters passing through, not caring for their environment. The whole place starts to deteriorate, and that is slumification. And so you end back at the point where now this place is an undesirable neighbourhood and the property prices fall, and you can now start to get the young professionals once again saying, oh look, in this neighbourhood, they're handsome old houses, but they're very run down. The property prices are cheap, but we can move in there and do it up. And so the whole thing starts again. Well, Dendrinos has modelled that process as a kind of predator-prey dynamic like this. So, it's something like household incomes, the average household incomes in the neighbourhood, and the property prices. So when the property prices are low, it allows the household incomes in the neighbourhood to increase, because it means it can bring in these young professionals who will have potentially higher household incomes. So we're kind of somewhere down here. We've got low property prices kind of playing the role of the predators. And so the household incomes of people in that area start to increase. But as the household incomes increase and they're making it a nicer place to live, the property prices start to rise. And so you then start to get this situation of turning it into flats for renters, and the average household income decreases again as the renters start to move in. And that then causes the property prices to fall, and so we're back into this cycle. So yes, Lotka-Volterra is an alternative to simple harmonic oscillation as a potential model that we can look to when we discover evidence of cycles in our socio-historical data. We can, take this as a starting point and perhaps adjust it to see if we can fit whatever scenario we're finding. And finally, in this calculus lesson, we're going to look at a dynamical process we'll call overshoot. So empires, for example, don't oscillate. They rise and fall. They grow, then they overshoot some kind of limit of viability, and they collapse, and that's the end. They don't rise again. And this is related to something known as the Seneca effect, which is named after the Roman writer and statesman Seneca the Younger, who said that growth is slow, collapse is sudden. And I think he was thinking about something he'd heard about a terrible fire that destroyed the city of Lyon in Roman Gaul. And he reflected on the fact that it took decades, if not centuries, to build up Lyon as a magnificent, beautiful city. And the whole thing could then be destroyed in one terrible fire, lasting just a day and a night. So this is a point he's making, that to build things takes a long time. To destroy them can happen overnight or in a generation. So one way to reproduce this Seneca effect is to start with the Lotka-Volterra equations and adapt them a bit. So let's have a look at that. Okay, so this was our basic Lotka-Volterra equations. X dot equals x into a minus by, y dot equals y into cx minus d, where x was prey and y predator. And in fact, if we look at the kind of chart we get with just even these basic Lotka-Volterra equations, it does tend to look like something like that. The evolution of the prey population, there is a kind of slower build up and then a more sudden collapse, but we can exaggerate it to make a slower build up and a more rapid collapse by modifying these equations, firstly by adding another species whose population will be represented by Z, so we're interested in Z dot. And this is known as the parasite species. When we introduce Z, firstly, the equation for the prey remains the same. It's just affected by the predators and itself. But the predator now is considered to be preyed upon in its own right by the parasites. So we adapt this equation. Firstly, we make the D positive. So now the predator population has a natural tendency to increase, but it is decreased by the parasites, which, you know, do nasty things to the predators and cause them to die. So we subtract a term, E times Z, where E is just a constant. And then for the parasites, we just think of them as like we used to think of the predators. So again, their population increases proportional to the existing population of parasites. And it's increased by the availability of predators. So there's a constant F multiplied by the population of predators. So the more predators there are, the more the parasites can breed and infect them, and the population of parasites grows. But the parasite population also has a natural tendency to decrease. So we have a minus G. So, you know, if there aren't any predators for the parasites to infect, then the parasites will die out. Well, if we take that set of equations and plot what happens to the prey, so that's this, the prey in this model now with 3 species. So we've got a Seneca effect. We've got this long, slow build-up and then a rapid crash by introducing this parasite species. And so we've got seemingly an example of an overshoot, and one that also exhibits this idea of slow growth, sudden collapse. But the trouble with this is, though, that if the equations, we can still keep evolving forward, and we'd find that it repeats, just like the original Lotka-Volterra. We'll get another one of these. And that's not really what we want, because we said at the beginning that empires rise and fall, the end. There is no repeat of it. So what we have to do is say, well, you know, that reproduces the overshoot, and we just ignore what happens after that. We just assume that once it's collapsed down to here, that's the end of it. Now, Peter Turchin has developed another model of overshoot, which I'll write up. Okay, so in Turchin's model, what he's concerned with is the area of an empire and its asabiyah, using the term from Ibn Khaldun, which means something like social cohesion. And he uses A for area and S for asabiyah. Obviously, they both begin with a letter A, so he had to choose a different one. So it may be because it's the second letter of asabiyah, but also, you know, it could stand for something like solidarity or social cohesion. And these are his, you know, rather complicated expressions for how the two vary over time. You know, I don't want to go through in detail, just want to illustrate the principle here that we can develop this kind of, you know, we can develop models, idiosyncratic models to study things like overshoot. Obviously this is, you know, a much more specialized than the things we were looking at before, like harmonic oscillators or exponential growth. To get this kind of overshoot, we're having to, you know, develop quite intricate sets of equations. You know, in the right place, we will, of this course, we will come on to looking at his particular theory of it. But what he's basically saying is that the area increases in proportional to the existing area. So the bigger the empire goes, the more powerful it grows, the more powerful it is, the more it can expand. But it also tends to move towards some kind of limiting factor. So there is a kind of logistic type term in here. And it also depends on the asabiyah, because if there's a lot of social cohesion, a lot of solidarity, a lot of asabiyah, then you know, the empire is vigorous and will expand against its neighbours. But if there's a lack of asabiyah, if the population of the empire you know, is not loyal and committed to it, and is just selfish and is not civically minded, then the empire is going to find it harder to expand. It's going to be weaker. So there's an S factor in there. And then for the asabiyah, the key point is that as the, well, asabiyah tends to increase logistically up to some limit from that, but it's also affected by the area in that the area appears negatively in here. So that as the empire grows in area, particularly the people in the middle, where it's relatively peaceful, lose their commitment to the empire. They become more selfish, more just concerned with, you know, easy living. And so that factor tends to reduce the asabiyah. So so the empire, if this was all that applied, the empire would just grow and maybe reach some kind of equilibrium. But because of this tendency of the asabiyah to decline as the empire grows in area, it can get to the point where it's gone too far, because asabiyah is still declining, and now the asabiyah isn't enough to support an empire of that size, and it collapses. That's the basic logic of these equations. And if you actually simulate this and plot the results, you get something like this. Okay, we're here plotting the area in black. So the area of the empire, so it you know, kind of exponentially grows at first, and then it reaches a sort of high point. Meanwhile, the asabiyah is increasing in this empire. As at first it's still quite vigorous, but then here, when it's got large enough, the asabiyah of the people, particularly at the centre, starts to decline, and so the average asabiyah of the empire is decreasing, and this declining asabiyah causes the area to start to collapse. Now, the more the area shrinks, the less powerful the empire is, so the less capable it is of, you know, keeping itself at that size, and it's going to tend to shrink further. Now, it wouldn't shrink if the asabiyah was still strong, but the trouble is that the asabiyah has also been declining. And if the values of these constants here, little a and b and so on, have particular values, if the constants have particular values, you can get to the situation where even though the area has shrunk enough that the asabiyah starts to grow again, it's too late, and the area now is just collapsing exponentially, and it reaches zero before it can start to turn up again. And when the area of the empire reaches zero, that's the end, it's collapsed. Now, though, as with this, we could evolve these equations forward beyond this point. and I can't quite remember actually what happens, but I think, you know, area tends to keep decreasing, and it maybe shoots off to negative infinity, or it turns around and goes to positive infinity, something. Asabiyah, you know, will tend to keep increasing there. So this model could be evolved forward, and it would then lead to unrealistic results, you know, because area can't become negative. So we just have to say that the model only applies up to this point, just the same as here. It applies up to there. What happens afterwards? Well, the model predicts various things, but that's unrealistic. That, you know, we ignore that, and we have to do the same here, which is, you know, which is fine, but it's not entirely satisfactory. It wouldn't be, you know, very satisfactory in physics if we had the, you know, the laws of physics, equations of physics, and we said, well, it applies up to this point, but you know, what the theory says happens after that, you just ignore that. You know, it's not right. But it only goes up to this point. Now, admittedly, in fact, in physics, I think situations like that sort of can occur sometimes, but it's not really satisfactory, and it suggests, you know, you haven't really got a model that really faithfully reproduces what's going on here. If you have to, you know, just say, oh well, we'll ignore what the model predicts after that. So I think what we're seeing here is how we're coming up against the limits of what calculus can do for us. When we're looking at things like simple harmonic oscillators and exponential growth, those kinds of things that are also found in physics, that works. But when we're looking at things like this overshoot that we get in, particularly in socio-historical processes, and maybe don't have particular counterparts in the physical sciences, then calculus isn't really properly working for us. We need some other kind of mathematical framework to deal with things like this that isn't calculus, and you know, maybe some of the tools that are being developed in complexity science are sort of moving towards that, but even they you know, haven't yet really been able to reproduce this kind of thing. So it's something we still don't have the mathematics for. We're kind of waiting for the mathematical genius to come along, who will develop a whole new sort of paradigm of mathematics that's more suited for dealing with these kinds of problems that we get in theoretical history, the Seneca effect and overshoot and collapse.